So this is kind of what we showed, the one with the guy on his back with two canisters. We showed the jet lev. I guess there's some kind of power or fuel pack on the back, but all the action is the two jets that are on each of his arms. Not sure how it works. I imagine it mixes two fluids or combusts two fluids to be able to do that. So it's not to be able to get 100 feet in the air. It's just to be able to get 10 feet above the ground and to be able to move much faster over difficult terrain. So same principle, I think, as the jet lev, except the jets coming out of it are different fluid. So instead of being 1,000 kilograms per cubic meter, it's about 1. The density of air is about 1.26, I think, kilograms per cubic meter. And yeah, so cool idea. And so it's for mountain rescue, to go and pick people up who are otherwise distressed, I guess. So what else have we got? So today we'll follow on. I mentioned what we would do, and we're following on. This is our last fluid dynamics Bernoulli session, weeks 4 and 5. And we'll talk about methods by which we can use Bernoulli to be able to measure flow rates. And so measuring flow rates is not so easy. You could imagine discharging this into a bucket, seeing how long it takes for the bucket of a known volume to fill, but that's typically not very convenient for us. And so one way to do it is to use Bernoulli, and instead of measuring a flow rate as an accumulating volume in a bucket, to measure a pressure difference between 2 points, and to try and use that pressure difference to be able to infer what the flow rate is. And so we can do it in an open channel. And so if if you're an environmental engineer, you might be sent into the woods to gauge the flow of this ephemeral stream that's running. And so what you do, you take a board with a notch cut in it, this size, and you stick it across the stream, allow it to build up behind, and then measure the depth to which it comes across the orifice as a proxy for the flow rate. And so we'll see how we can use overshoot or undershoot weirs to be able to do that. You remember we had all kinds of issues last time in getting my computer going. I did record it and I did save it, but it didn't ultimately save. So 5.2 is not online. It was lost. So no problem for most of you because you're here, but we have the one from 2016 instead. So anyway, I don't really have any comments for the good of the order. We have no class next week, as you know. The test is online. I'll sign on Canvas at 7:45 for those who want to be walked through the process or just want that security. It's good so that I can work out that everything works for you. No webcams are required. You don't have to be online. I want to migrate it to I will use chat during the test. You should ask questions. If I don't want to answer it, I'll say I don't want to answer it, but you should ask questions, chat to everybody, so everyone gets the question, everyone sees the answer. In the future, I want to probably migrate just to chat on Canvas. Canvas instead of Zoom. Did I say Zoom? I'll be on Zoom at 7:45 and Canvas. But I think for this first one, it's probably easier just for me to be on Canvas. I'll be on both, actually, so you can ask questions either way. You know the deal from the emails, hopefully. Do the practice test just to see how they work. I don't know what else to say other than that. It will open at 7:55. It will close at 8:31. Typically, you'll get a warning. Anything you haven't saved in Canvas by that time will automatically be taken as given, so you don't actually have to press the submit button. It will do that automatically when it closes. So, questions quickly? Yeah.
So you said the exam is completely online. Does that mean you still have to come to the classroom?
No.
No.
You're welcome to come here. Probably decent connection, but you're welcome not to. And no webcam. It's on trust, and so that's the deal. How trusting I am. So, yes. Normally not, but I personally wouldn't be too worried about that. Question was, should you be completely off the internet? You should really only be on Canvas. I don't want you conversing with people. That's the main issue. Yeah, I probably prefer you don't do that. But I think you know the format for this, and I've explained that instead of being this long test as it has been in the past, it's a shorter test, and so it's a bit simpler, more rote in terms of calculate this number, using this number that you've calculated with this other number you've calculated to do this. It's kind of set up so there are no things that you have to do where if you got the first part wrong, that all of a sudden everything else goes wrong. So I try and accommodate that. And so, but it is kind of rapid fire, and so you need to have things in order to be able to do that. So I guess what I'm saying, it'd be useful to make your own equation sheet, so you have it right there in terms of things. Certainly you can use the old tests, and those work through problems that will be like the problems we have, but there will be no problem that's a direct repeat of those. But there are only so many, I'm only smart enough to figure out bizarre problems, so many of them. There is an infinite number of problems that it can be, but I'm not smart enough to figure what those infinite number are. So my point is that you probably have to have some things at your fingertips. So if you're searching, yeah, sure, you can Google for what the density of something is. Pretty much everything you need in terms of parameters you'll be given, because otherwise you can't calculate a number which is an exact number within 10%, right? That's what we have. And so it needs to be aware of that. Yeah.
Is it all going to be open-ended? Like, is there any multiple choice at all?
There are multiple choice.
Okay.
Yeah. So, the one way that I use multiple choice is that if there's a number that you've calculated from the previous two questions, and I can think that in the first test, then there's a multiple choice question, so you can test whether your number is correct, that then you have to use in the rest of it. So my intention is not to have follow-on questions, but I think it's not quite, it's inevitable, it has to be there, right? And so everything that you put in it, Canvas saves your numbers. And so if I make a mistake in the numbers, I can always go back and correct and credit you if I've done something foolish and those kinds of things. So yeah, it's not a perfect system, but nothing in life is perfect. I wish I was still in bed. You probably do too. Life's not perfect. Come on, smile. For Christ's sake. Any other questions? Okay. Any other questions online? No. All right. So, we're still with Bernoulli. So we'll talk about measurement today. And so I said before that when we talk about Bernoulli, 90% of the time we'll be talking about along streamlines. You know this arrangement in terms of writing it upstream and downstream. You ask questions about what these terms are. Don't worry about them. Pump head, losses due to viscosity. We'll deal with that in due course. We will think of this equation in terms of a total amount of energy. We'll call this today the energy grade line, what this matches. And so this is constant, and it's equal to a certain amount of energy all the way through our flow system, from upstream to downstream. And so we'll work with that to be able to explain what we're doing. We've talked about free jets, again, derived from Bernoulli, where you write it upstream and downstream, where the requirement is a big tank, so the upstream velocity doesn't change, and it squirts out. This is the streamline velocity always, and so the stream could be directed downwards, it could be directed upwards as we talked last time, or horizontally. It will be exactly the same value for the streamline, but the components vertically and horizontally won't be the same, depending on its orientation, obviously. And we talked about continuity, and that is merely saying that if we have only four knowns in our Bernoulli equation, we can write the velocities by linking them to each other if they're in line with each other within straddling a stream tube. And that allows us to solve a problem where we have two unknowns of velocity, apparently, because the velocities are linked to each other. In your future life, you'll use this in terms of the densities. So it's really what's called a mass balance in the equations for flow in porous media, for instance. We always take the densities upstream and downstream to be the same, so they cancel out and we don't have to worry about it. But that's the more correct way of writing it. Instead of a volume rate balance, it's a mass rate balance in terms of kilograms per second. And so today we'll talk about flow measurements, as I mentioned. And this should be pretty easy going. We'll talk about the two cases we just looked at in videos. The last one was the Venturi meter and its derivatives. And the earlier one was open channel flows using a weir to be able to measure it. Quite standard ways of doing it. I'll probably rely on my horrible notes to do that today rather than scribbling things just because they're there. And just to be able to describe the system. So the system is essentially this. We have a flow through a constricted pipe. It contracts to be able to accelerate the flow. So clearly the flow across this area, A2 and A3, is going to satisfy A2 V2 is equal to A3 V3, as we have. We know that from upstream to downstream, I said that our energy grade line, didn't like that, energy is constant. This is constant. And so the elevation of all of these are constant for this easy example. So if we look at Bernoulli between upstream and downstream, this would be equal to our EGL, our magnitude of our energy. Ignore this for the moment. And so this means that if we change the velocity of flow, so if velocity 2 increases relative to velocity 3, then by definition the pressure here will decrease. And so if we measure the pressure at point 2 versus point 1, then maybe we can use this value to be able to figure out what the change in velocity is. And not only the change in velocity, but the absolute velocity. And so this is just what the pressure along the length of this tube would look like. Upstream, it's the same as the downstream. So if this diameter here is the same as the downstream diameter, then by definition, the velocities V1 has to equal V3. If V1 equals E3, then P1 equals P3. But if velocity 2 is less, then the pressure has to go down to accommodate that. If it's flowing very slow, then it will do this. If it's flowing faster, then it will go down more. And if it's going really fast, it will get below the vapor pressure of water. And the vapor pressure of water is something like 0.6 psi. Atmospheric pressure of water is 14.7 psi. I promised never to work in imperial units. So this is 100 kPa. And so this is a half of this, so it's about a 28th. So it's about a 30th of 100. So this is, I suppose, about 3 kPa. Absolute. Don't forget to use absolute pressures in using the ideal gas equation if you need to use it on Monday. So this is essentially 0, and so this is probably very low here. But if you go fast enough, then you can get below the vapor pressure. If you get below the vapor pressure, the water will just turn to vapor. It'll turn to bubbles. And it won't get below this because it can't get below those easily because it'll just turn into a water vapor. So this is the reason that the turbines, the blades on deep sea submarines with nuclear weapons on them, kind of a topical subject all of a sudden, unfortunately, are big and rotate very slowly because if they rotate very quickly, the pressures on the blades can get below the vapor pressure. If they get below the vapor pressure, they make bubbles. The bubbles, when they collapse, when the cavitation, it's called cavitation, the bubbles collapse and they make noise, and you can hear where the submarine is, and no longer are you running silent and running deep, as the term goes, and you have to worry about being tracked by the networks of hydrophones that are all around the world that track these things to make sure everyone knows where all these things are, or some people know where these things are. And so that's the idea. These Venturi meters can be the best, as we've just seen. They can also be just a constriction in the flow. They're not so useful if they're just a constriction, because you violate some of the tenets of Bernoulli, which is this no vorticity. And the solution for this would be to take, in this case, the upstream pressure measured on the wall of this here on the streamline, and the Venturi pressure measured right here on the wall as well, perhaps with a manometer or perhaps with a pressure gauge. And we assume that it's horizontal to make life easier. If that's the case, this is upstream Bernoulli, this is downstream Bernoulli, not written in the way I like it as a length, but written as a pressure, both terms. We use continuity to link the two velocities in the upstream and downstream together. So now we have a linked velocity and two pressures that we've measured. And so we can use that to be able to figure out exactly what the linked values of velocity are. I won't go through the math that can do it. Hopefully you're trusting me by now, but it comes down to being a flow rate, which is equal to, I guess this would be velocity 2 times area 2, which is going to be the same as velocity 1 times area 1. I'm guessing it's that V2A2 because A2 is in here. So I suppose if that's the case, you could surmise that this parameter in brackets is actually V2. And if you measure the differential pressure, not the absolute pressure, the differential pressure, you can get, with a correction factor for the areas and the density of the fluid that's flowing, you can get the flow rate. That's it. Nothing more involved in this. I think a very interesting thing to notice is that this only relies on the differential pressure. And so if you want to measure the pressure at point 2 and point 1, you could use a pressure gauge that measures pressure 1 and pressure 2, but that's not very accurate because pressure transducers only work over a certain range, and maybe they measure to 1,000th of that pressure range. So you can get values for those, but it's not as accurate as using what's called a differential pressure transducer. You can buy them. They use PZTs, and what they do is they link the two locations, upstream and downstream, and physically give you a readout electronically of the difference in pressure, delta P, not the absolute pressure at those 2 points. And it turns out to be much more accurate to be able to do that. The problem is if you go up above a differential pressure that's large, then you can bust them. And we bought one for our lab a couple of years ago. It was $1,000. So it's more expensive than a $50 or $100 pressure transducer to be able to do that. So that's it. And so an example. So a quick example before we start talking about open channel flows. So an example where we have water flowing in a pipe, kind of a Venturi meter, has a different diameter here from here. It truly is measuring the differences in pressure in an upstream location where it's slimmer and a downstream location where it's wider. I guess it's not water that's flowing. It's something that has a specific gravity of less than that. So I guess the fluid is equal to the unit weight of water divided by SG, not that, times SG, specific gravity. So if its specific gravity is 0.5, then the fluid you have is half the density, half the unit weight of water. That's what it means. And so we have ability to get this because we know that water is in the tube, but the other stuff in this pipe is going to be the flowing fluid, right? The white fluid in this particular case. And so what do we do? Well, we can write Bernoulli for that particular case. If we write Bernoulli between points 1 and points 2, you can see, yeah, you can see. It's not super thick font. So what do we know? We know that at this point here it stagnates. So you can imagine the water comes here, stagnates, the velocity is 0, and then goes around it. So by definition, we know that P1 not equal to 0, but V1 equals 0. I'm going to use this, I think this red one's a bit more blunt. So we don't know what P1 is. We know that V1 is equal to 0. We know that the elevations of points 1 and point 2 are both equivalent. So we could do this in the way that I usually do it, which is that they both go, they're not 0, but they both cancel out. P2 is measuring the pressure here. We don't know this. And we also don't know the value of velocity 2. So what do we know from using Bernoulli? We have pressure and velocity. So we can rearrange those three terms to get this term here in terms of the change in pressures relative to the velocity. We know that the unit weights or densities that we have are for the flowing fluid, not for the gauge fluid in the manometer. And so we end up with this expression. So this is one fundamental expression that we have. So unfortunately, we have three terms. And we want to be able to have another equation to close it, or two equations. But we know that we only need to know the difference in pressures, not the absolute pressures themselves. And so what we could do is we could write the manometer equations. And so the manometer equation is going to be what? Perhaps I'll go back to my not so blunt instrument. So what do we do? P2. So we could start here and work our way through the system. So as we go up, we subtract pressures. So P2 minus, what's this? This would be L. It's probably a more complicated example than I want, really. So we need to go up to this point here. So P2 minus unit weight of the flowing fluid. I guess I'll just write it as unit weight, since we have unit weight of water, multiplied by L plus H. That gets us to this point. We know we can go across the fluid to this point. Now we need to come down to here. So we go down plus H times the unit weight of water. Gets us here. We can go across here at the same pressure. We can go across here at the same pressure, plus L times the unit weight is equal to P1. We can subtract P2 off both sides. And now we have this term here. We could divide both sides through by the unit weight. And we have this term here, which is exactly equal to this, which has to be equal to V2 squared over 2G. And of these, I think we know everything, right? We know that the unit weights, they're linked by, this is 1 actually. This is easy. This is also 1. We know that this is equal to SG by definition. And we know what these lengths are. We're given these lengths. So that's it. So that's the simplest way to go through it. So I guess it's interesting. We have three unknowns, but really we only have two unknowns that we need to solve for, because we know that the difference in pressures is all we need to be able to describe this velocity. It's not absolute values. So if this is 1 and 10, or if this is 91 and 100, we get the same result. It's just the difference in these. Okay. That's it. And it's the solution's there. The solution's written in a much more difficult way, I think, but it's the same idea. So, same idea if we want to be able to measure flows in the field. As I say, it wouldn't be an unusual thing for someone to go, some of you in your majors an environmental systems engineer, mining engineer on site to go out and measure flow within a small stream. You take a board with you that has either a V notch in it or a rectangular notch. This one is actually an undershot, so you turn it upside down so it flows under. Usually you have it as overshot, so it's a V that's in the top of the board that you put on the stream. I should probably show a picture, but I don't have one really at hand. And how do we solve this? So I guess just to make sure you know what the geometry looks like, is it's a board that looks like this, with a slot in it. It's the same as the picture we just looked at in terms of the numerical model. And so it would be a board that you'd have that you just jam across the stream. You jam this into the banks and the ground so it completely blocks the flow. And the only thing it has to do is it would rise slowly to a height here, and you'd use that height, and we'll look at that later, right? This is the idea here. But this is the same thing. We can use Bernoulli again. So this is the weir that goes across the stream, which is an undershot weir for obvious reasons. I don't know if they use them for weirs. They use them for water wheels. An overshot wheel is where the water comes onto the top of the water wheel and it turns this way as it lands on the top of it. An undershot mill is where the water comes underneath it and pushes the mill along without it using its weight to drop. And so what do? We write Bernoulli's equation from point 1, which is on the upper surface, to point 2, which is downstream. We assume that point 2, the height is roughly equal to the opening, not quite, but roughly. If we're writing pressures on the surface, then pressure 1 and pressure 2 are both atmospheric. Velocity 1, well, definitely easiest for us to use the big tank assumption. And this is moving at a very slow rate in this direction. So it's certainly not being drawn down, but also it's not moving very quickly in this direction, V1, which is the streamline velocity. So it's about equal to 0. They're not at the same elevation. And of course, we can't throw those away this time. In fact, for something that isn't in a pipe with a pressure upstream driving it, it's purely gravity that's driving it. It's the change in potential energy between the upstream and the downstream which is driving it. So it's this term, Z1 and Z2, which is driving it. So we do the same as before. We write continuity in terms of the cross-sectional area upstream and downstream. Cross-sectional area upstream is going to be Z1 multiplied by the width. It's this area here. So this is area 1, which is B times Z1 times velocity. And downstream is exactly the same, as you can appreciate. And so we have continuity. We know that the product of these, area times velocity, is meters cubed per second. And so we can just substitute into Bernoulli. We don't really need to do it this time in terms of this velocity. Well, I guess this is actually done not assuming this. So we haven't restricted by that assumption. We've linked it in these ways, and you can tell it because of this would be the difference in pressure upstream to downstream, and this would be the difference in areas upstream and downstream, just like it was in the Venturi equation. And it works out to be this. And so you'll notice some similarities. Presumably, as Z1 gets to be very big, very tall compared to this, then this really is the big tank approximation, because you have a huge volume upstream and only a very small jet downstream. The rate at which this small jet can deplete this is very slowly, and therefore if Z1 is big and Z2 goes to 0, this term goes to 0 and this term goes to 0, this term on the bottom goes to 1, and you just end up with this. And of course, this is very familiar to you. This is the free jet equation, right? Remember, velocity of a free jet is equal to 2gh. And that's exactly what this right term is. So this is velocity, V2, and this is area, A2. And so we're not making any assumption. We're measuring this height. It doesn't matter that it's approximately equal to this, but we're measuring this height and then using it in the equation to get the flow rate. So that's the deal. If we wanted to, we could just measure the upstream depth and know what this separation off the bottom is and try and calculate it for that, because typically the value of A is close to being Z2, as you can see here. Not exactly. There's an effect called the vena contracta, and I suppose contracta means obviously that it gets smaller, and vena, I don't know what it means in Latin. Must be the jet or something, like as in Venturi, perhaps. Venturi is someone's name, I think. I'm not sure. And so it's roughly the same. And so for values where this is, for different velocities, we can use the correction factors to be able to figure that out. We won't care too much about that in this class. You can go to a reference text and figure that out. So that's for an undershot weir. For an overshot weir, such as this, or a sharp-crested weir, then perhaps the analogy with a free jet is much more apparent. You have this flow. You can imagine that the flow was completely horizontal until you get to this point, and then it goes on some other trajectory as you go downstream. But the reality is, because of this vena contracta effect, you have this dip. No, at least my internet's working. And the velocity across here is not constant. So that's a wrinkle, I guess, on Bernoulli. We kind of need it to be constant. You also get this separation. And so you could imagine that if you thought that the top streamline was this streamline here, and the bottom streamline was this streamline here, which I guess if it was a very low creeping, very slow velocity creeping flow, that would be it, then you wouldn't have this portion opening up. The reality is that you get this separation, so-called separation, at this interface. Go to Talleyrand Park in Belfont and see the waterfall. It looks illuminated underneath the water because where the water comes across this stepped waterfall there's the sunshine is reflecting off a surface down there, and you can actually see this separation underneath each of the little portions that's coming off. It's at the crossroads in Belfont, if you ever go into Belfont. And so this separation makes it look really like a tank, right? It's not really very different from if we drew our tank free to look like this. Where this is V1 and this is V2. And a streamline going through there is doing this. So it's similar to that. And so it's not surprising then that we could characterize the velocity that occurs at this point as equal to some height. And so because it's this velocity 2 is equal to 2gh square root, this would be uppercase, lowercase h, right? So we'd expect that this is proportional to that in some way as an engineering approximation. So what we need to look at is what would be convenient to measure here. We've put this across the stream. It might also be a weir on the Allegheny River, which is a permanent weir, which is running all the time. And if that is, then this is a concrete obstruction, and we would have a gauge at the side to measure the flood stage or the water level, and that would give us directly the flow rate of the river in cubic meters per second or cubic feet per second. And of course, that's how they do it. If you see by the side of streams, I know there's a back road to the airport on Spring Creek. There's a little corrugated circular cylinder that's pushed into the stream. It comes out of that with a little box on top, and it's got a a solar panel and a little telemetry aerial antenna on it, that's a stream gauge. All it measures is with a pressure transducer or with a float, the height of the water that's in the stream, because there's direct connection between that little vertical corrugated pipe and the stream, so it mimics exactly the rise and fall of the stream. It measures that pressure as a depth, and so it knows this height relative to the magnitude of this. So if you take the height of the upstream location relative to the crest of the weir, then you convert this being equal to some correction coefficient. If you look at the volume as being equal to the velocity multiplied through by the area. And so, of course, the area is going to be this. This is B wide and H, uppercase H high, right, from this. Nothing more than that. And therefore you can get this. You have both of these terms here, both inside, sorry. You have these terms here, both inside and outside the bracket. And therefore you can take them outside and it becomes this. And so the idea is that if you know what this correction factor is, probably it's going to be close to 1. If you know the width of your flow, if it's not all the way across the river, it'd be the river width if it was across the river. If it's a notch, then it would be the width of the notch. If it's a triangular cut, triangular V, it would be a different coefficient, but it's calculatable just straightforwardly. You know what planet you're on. You know the height of the water in the stream. And as they say, Bob's your uncle. You have the flow rate. And so that's why if you're a kayaker and you look up the stream gauge locations to see if the river's flowing, it'll tell you what the velocity, the flow rate is. And if you then go to American Whitewater for all the rivers in Pennsylvania and around the US, it will tell whether it's runnable, dangerous, not runnable, etc. Because they know empirically what the river flow rate has to be to make it a viable flow rate. We're doing well. So I said it was going to be a leisurely stroll today. Any questions? No. Okay. It's not super challenging today. So we mentioned the idea that in going from upstream to downstream, we use this concept of the energy line, energy grade line. And so that just means that in this term, or this equation Bernoulli, the reason we can write it upstream and downstream, and at any point along a streamline equating to the same magnitude, is that along the streamline, the energy is constant, and probably not the H. And so we can define two parameters. We can describe the energy, which is all three of these terms together. These aren't units of energy. Energy would be joules, which is Newton meters. So these are units of length, so they're not Newton meters. But I guess this is energy per unit volume. Per unit volume of water. And so Z is energy per unit volume of water. It's potential energy. So it's the height of the water above a datum, and it's that height multiplied by its unit weight. But if we divide height by unit weight, if we divide height times unit weight, which is energy, by the unit weight, I think actually might be the unit weight or the volume, then we end up with the length. I won't do the conversion here, just because it doesn't matter. Obviously it's units of length, but it's a proxy for energy. It scales with energy. Potential energy, pressure energy, kinetic energy. So this half V squared is kinetic energy, right? That's exactly what this is. So there's no accident that it looks the same as kinetic energy. The other term that we can use is if we just take the fluid parts and describe these as equal to head. And head is just equal to the pressure head and the elevation head. And this is the hydraulic energy. I guess it is I think it is, can't remember whether it's unit mass or unit volume, so it doesn't matter. But this is what we classify as the hydraulic grade line. And so these two lines are useful to try and understand exactly what the flow is. And so we know that we are constant magnitudes of this total value as we go through a system. So what we're just trading is changes in the magnitudes of these as we go through the system. And so if we take a simple flow system with a large tank with a pipe in it that contracts and then goes out at atmospheric pressure, we can chart all the components of Bernoulli as we go through from upstream to downstream. And when we're upstream, there's no velocity. The pressure, if we look at the streamline on the top, and we're going to take this streamline as we go through here. So think about the top streamline. We can think about it going through the middle, but it really, I suppose, would be along the top of this. It doesn't really matter. So by definition, the Bernoulli head E here is equal to Z. So this is the energy line, which is constant throughout our system and includes the three components of Bernoulli. If we go to this point here, point 3, what do we have? We know that the pressure here is 0 because it's coming out of here. We know it has some velocity, which is V3, which we don't care where it is, but it's finite going to be. And we know it's at some elevation. So then we know that the point that represents, if we're working up from this as this, I guess this magnitude here is equal to E and H, right? These two values. Then we know that the total energy is equal to the two of these. Pressure has to be 0, so it just doesn't exist. And so de facto then, since this is taken outside our hydraulic grade line, everything below the velocity squared term has to be our hydraulic grade line coming through here. So this red line is actually our HGL as it's marked. And so now if we go back to this point, what do we know? We know that this has an area A2, this has an area A3, and we know that V2A2 is equal to V3A3. We therefore know that the second velocity is equal to just the ratio of those areas. And so we know de facto that this is not 0. But we also know that it's less than velocity 3 because area 2 is larger. So this is less than 1. And so V2 has to be smaller. And so this value has to be smaller than this value. And so now the hydraulic grade line. So we now know, if we know what this velocity is, which we can calculate because we know everything here, we can calculate this velocity. And we know this height of this location, Z. So now we can calculate what this value is. So it's actually kind of an exposition of exactly the example we didn't get round to doing on Wednesday. And you'll remember a figure, I talked about it in terms of I can't remember what I called it. Did I call it the silent killer or the resting giant? It was this example with a nozzle with fluid coming out of it, a pressure in here as P1, a velocity here as V2, V3, and a pressure here as P2. And we didn't go through it, but I said it's the same as having a gas cylinder in the lab. You don't tether it properly, it falls over, it knocks the top off, and it acts as a rocket to go through the block wall in your lab and 2 block walls away from you with incredible energy. So this is an analog for that. A closed volume with a given pressure inside it. We said it doesn't satisfy Bernoulli strictly because it's not steady state. This is a finite volume. You open it, you allow it to run for a minute. Sure, the pressure's still 100 megapascals in here. But if you look at it a day later, there's no pressure left in here. It's just like puncturing a tire. So we can't strictly use Bernoulli for it, but we kind of can, and we get a good result. So this example is a bit like this. We have an upstream pressure. We have a downstream velocity. We use the upstream pressure to be able to, with the downstream velocity, calculate this velocity here. Once we have this velocity constrained, we can use this upstream pressure, known downstream velocity, to calculate the intermediate velocity here. And as a result of this, we can also calculate the pressure. We have to do it in a two-step process. So this is exactly the same thing we've done. I'm not talking about it for that reason, but I'm talking about it for the difference between energy lines and hydraulic grade lines. But that reflects on that. And the working is there to be able to figure that out. And the one consequence of that, which I think is kind of an interesting consequence, is to take it the next step and to now draw the energy lines, the energy grade line, and the hydraulic grade lines for this particular example. So here we have exactly the same problem. Here the pressure is equal to 0. Here the velocity is pretty much equal to 0. And we know the elevation. Here the pressure is 0. Here the velocity is not equal to 0. And we also know the elevation. So we know everything upstream. There's only one thing we don't know downstream. So we can calculate the velocity. So we can get this magnitude here. We know by definition that the velocity head must take up this full amount here. V squared 3 over 2g. This full amount must be equal to the elevation because we know that P3 is equal to 0. And so by definition, this must be the hydraulic grade line. And so how does the hydraulic grade line go back to here? Well, the other thing we know also is that if we take a point at this, which let's call this point 3, this point 2, then the velocity at point 2 times the area at point 2 equals V3 times A3. So this is constant velocity all the way along here. Has to be by de facto because the cross-sectional area of the pipe is not changing. So that means then if we look at these values as we go to these different locations, this one's the easiest one to do. This will be the elevation. To get to the hydraulic grade line, we have to add the pressure because together these two values equal H. And to get to the energy grade line, these three values are equal to E. So that's pretty straightforward. But the funny thing comes is when we go to this point here, which is above this outlet. And that is that all of a sudden we still need to do this. We still need to link the pressure into this point. But of course, this point is already at this elevation, which is this full height. And therefore, to get back to the hydraulic grade line, we have to go down. So these pressures are below atmospheric. So this is atmospheric here, this is subatmospheric. And so what you could do is if you had a long enough tube, you could put it up like this. And if this height here is equal to atmospheric pressure, then this water going up here will cavitate because the pressure in this water, just like the case of the vena contracta that we talked about before, is so low that it will approach the vapor pressure and it will turn to vapor. It'll cavitate. And so in the same way that we talked about this is absolute pressure would be 100 kPa. This would be 0 kPa absolute, and this would be 3 kPa, as we said here, right? And so in this particular case, in gauge pressure, if we wrote this for this, don't go. Sorry if I'm making your necks hurt. Then this pressure here would be 100. P3 is equal to 100 kPa gauge. And so we would want to get this pressure down to 3, essentially 0. So in other words, 100 kPa is when the pressure here is 0, and the pressure here is equal to 100 kPa. So if you want to de-air water for experiments in the lab, take the dissolved air out of your system, then what you can do is you can get 30 feet of Tygon, 60 feet of Tygon tube, run it up 3 stories, right? 1 story is 10 feet, roughly, and then make a siphon. Put it in some water, suck very hard to get it to go, or actually easier, just fill it, take the middle point of it up 3 stories with your thumbs across it, and then you have it filled so it goes up. You put it into a beaker at this end, slightly below the level at this end, there's a siphon, and then you have the water go up through this. When it starts off at atmospheric pressure on the left-hand side, it goes up through, becomes 0 absolute at the top. The water comes out of solution. You put a little bottle up here that allows it to go into there, and this bottle fills up with air as it cavitates, and then water comes down the other side into your beaker. So that's it. That's it. So that's what we've talked about. I guess we won't talk about anything next week, but there will be things online. These last things are talking about the limitations of Bernoulli when it doesn't matter. I think the only one we care about is the trivial one, and that is the one that we kind of didn't talk about, but I think you all kind of recognize, is that if you do the truck at San Francisco Airport and you have the plane blowing on it, then if you look at the truck, the flow around the truck is absolutely steady state. Look at it at second 1 and look at it at second 100, the flow lines look the same. If the truck is moving in static air, as you'd like it to do, if the truck moves through your field of view, it definitely is steady state. But if you're attached sitting on the hood of the truck, looking at the streamlines, then it's the same as the truck being static and the air flowing around it. And so the air on a plane, when you're sitting in the plane and the airflow over it, is the same as an airfoil in a wind tunnel when you're attached to the static thing. And so for Bernoulli, the flow regime can't be changing with time, and so both of them, you just change your frame of reference to be able to do that. And so, so we finished Bernoulli. Next 3 sessions, 3 weeks, we'll talk about conservation of mass, continuity equation, conservation of momentum and energy. That'll take us the first 3 weeks.